Hello. In this video we are going to look at why we need to introduce pairs of random variables and the business of correlation. By watching this video you should learn how to explain why and when we use pairs of random variables, you should learn to explain what it means when we state that random variables are correlated, and you should learn how to derive the Cauchy-Schwartz inequality. Before we get onto that though, let's briefly review what we have learnt elsewhere about pairs of random variables. In the videos on Bayes' theorem and independence, we learnt to think about dealing with pairs of random variables in the way that I'm about to illustrate. We drew a horizontal line and used this to represent the various values that the first of our random variables, capital X, can take. In this case, we have decided that capital X can equal either 0 or 1, and as such we divided this line into two segments. The length of this first segment was then made proportional to the probability that x equals 0, while the length of the second segment was made proportional to the probability that x equals 1. When we introduced a second random variable, we introduced a second line that was drawn perpendicular to the first as shown here. Once again, we saw how we could divide this line into two segments with lengths proportional to the probabilities of having y equals 1 and y equals 0. To talk about the probabilities of pairs of random variables simultaneously, we saw how we can divide up the plane into regions with areas that are proportional to the having particular values for the random variables x and y. In the diagram shown here, the shape here has an area proportional to having x equals 0 and y equals 0 simultaneously. The shape here has an area proportional to the probability of having x equals 0 and y equals 1 simultaneously. This part of the diagram has an area proportional to the probability of having both x and y equal to 1, while this final segment has an area proportional to the probability of having x equals 1 and y equals 0. We have discussed that the dividing line between the y equals 0 and the y equals 1 parts of the diagram does not have to go straight across. This line only goes straight across if the two random variables are independent. What we have not discussed is why we need two variables at all. After all, we could redraw the diagram shown here using a single line divided into segments with lengths proportional to having x equals 0 and y equals 0, x equals 1 and y equals 0, x equals 0 and y equals 1, and x equals 1 and y equals 0, as shown here. Furthermore, we could relabel these segments using a single random variable capital Z, which can take one of four values, 0, 1, 2, and 3, as shown here. Why then have two random variables at all? The answer to this question is that we need pairs of random variables to determine how the outcome from one random event affects the outcome from a second different random event. In particular, for many problems, we write a random variable capital Z as a linear function of two further random variables capital X and capital Y as shown. When we write expressions like this one, we say that Z and X are correlated and that Y represents some random noise. Let's look at this business of correlation in a slightly different way. Let's suppose that Z was equal to alpha X and that Y is always equal to 0. When this is the case, Z would be proportional to X, and as shown here, if we plot X and Z on a graph, the random points we generate in the XZ plane all lie on the straight line Z equals alpha X. When Y is non-zero, these points will thus be distributed randomly around the line Y equals alpha X, as shown here. The rest of this video is concerned with the derivation of an important result that concerns the degree to which two random variables can be correlated. It turns out that the degree of correlation between two random variables must be within certain fixed bounds. Before we get on to this proof, though, let's just try and convince ourselves that there must be some limit on the degree to which two random variables can be correlated by considering some of the geometric arguments we have made in previous videos. The first of these geometric arguments is based on this diagram that we've already introduced. Remember that the rectangles in this figure have areas that are proportional to the probability of having x equals 0 and y equals 0, x equals 0 and y equals 1, x equals 1 and y equals 0, and x equals 1 and y equals 1. Unlike the previous example that I drew, in this video the lines in the diagram go straight across and straight up, which tells us that the random variables x and y are independent. As we have seen, however, we can move these lines up and thus make y equals 0 more likely when x equals 1, and y equals 1 more likely when x equals 1. In fact, we can move these lines up so far that we can make it so that when y equals 0 whenever x equals 0, and y equals 1 whenever x equals 1, as shown here. When we do so, we say that the random variables, capital X and capital Y, are perfectly correlated. The events x equals 0 and y equals 0 happen concurrently, and the events x equals 1 and y equals 1 also happen concurrently. We can also move the dividing lines in the other direction as shown here. When we do this to an extreme, we ensure that y equals 1 whenever x equals 0, and y equals 0 whenever x equals 1. In this case, the two random variables are said to be perfectly anti-correlated. Hopefully, this figure makes it clear that the degree of correlation between two random variables must lie somewhere between these two extremes of perfectly correlated and perfectly anti-correlated. In case it is not, however, let's consider another geometric example. We now suppose that each random variable tells us about the random amount to move along a vector in the plane. In this case, the random variable capital X moves us along the line shown here, while the random variable capital Y moves us along the line shown here. It is interesting to think about the angle between these two vectors. Obviously, this angle must take a value between minus pi and plus pi radians, between 0 and 360 degrees if you must. If this angle is equal to 0, then the two random variables are perfectly correlated. If this angle is equal to pi by 2 radians, then the random variables are independent. And if the angle is equal to pi, the two variables are anti-correlated. The fact that two vectors in a space of any dimension must have an angle between them that is between minus pi and plus pi is a consequence of a theorem known as the Cauchy-Schwartz Inequality, this theorem is itself related to Pythagoras' theorem. Furthermore, there is a version of the Cauchy-Schwartz inequality that also holds for random variables, as we are about to show. To prove the Cauchy-Schwartz inequalities for random variables, we begin by introducing two real-valued random variables, capital X and capital Y, and one further random variable, capital Z, which is the function of x and y shown here, with alpha being a real-valued parameter. Now, because x, y, and alpha are all real numbers, the random variable capital Z must always be positive, as the square of a real number is always positive. As such, the expectation of Z must be a positive number. It cannot be negative, as the random variable capital Z is never negative for the reasons that I have just explained. We can write the expectation of Z as shown here. If we expand the brackets here, we get the result shown on the right. Furthermore, remembering that expectation is a linear operator allows us to rewrite this expectation of a sum as a sum of three expectations, as shown here. Remember, though, that the expectation of Z must be positive, and that as such the quadratic equation in alpha that we have just arrived at must be greater than 0. Right, so to summarize the argument thus far, we have arrived at the following a quadratic equation in alpha and shown that this must be greater than 0 for all values of alpha. In other words, if we plot the expectation of Z against alpha, the graph must not look like this. We know that the graph of a quadratic equation looks like this when the a parameter is less than 0. We thus know in this case that the expectation of x squared must be greater than 0. This is not surprising though, as x is a real valued random variable, and as such x squared must always be a positive valued random number. The graph of our quadratic equation for the expectation of z against alpha must also not look like this. That is to say, it must not have a region where the value of the expectation of z dips below the x-axis. To satisfy this second requirement, we have to ensure that the quadratic equation has no real roots. That is to say, there should be no values of alpha for which our quadratic equation equals 0. We know how to find the roots of a quadratic equation, however. We use the quadratic equation formula shown here. In this case, this equation will give us the values of alpha for which the expectation of z are equal to 0. We want these roots to not be real, however. In other words, we want these roots to be complex or imaginary. To get imaginary numbers or imaginary parts of complex numbers, we need to take the square root of a negative number. Hence, given that the only square root that appears inside the quadratic equation formula appears here, we must have that the value inside this square root must be negative. In other words, to have the complex non-real roots that we require, we need b squared minus 4ac to be less than or equal to 0. Let's now go back to the quadratic equation that we derived for the expectation of z. Inserting the values of a, b and c from this quadratic into the equality we just derived, we find the following. Rearranging this inequality gives us the Cauchy-Schwartz inequality that we require. This inequality tells us that the expectation of x times y all squared must be less than or equal to the expectation of x squared multiplied by the expectation of y squared. The equality here holds when x and y are perfectly correlated or perfectly anticorrelated. The inequality holds whenever x and y are not correlated perfectly. And that's it. Let's just briefly review the learning outcomes before finishing. Now that you have watched this video, you are hopefully able to explain why and when we use pairs of random variables, you are hopefully able to explain what it means when we state that random variables are correlated, and you are hopefully able to derive the Cauchy-Schwartz inequality. The most important result we have derived here is the Cauchy-Schwartz inequality. Thank you for your attention.